Hello everyone. I welcome you all to the e-videos prepared for an university syllabus under the Regulation 2021. Today, we are going to see the session on the topic thread issues from the second unit, Process Management, in the course CS 3451, Introduction to Operating System. Myself, Dr. Sirani. Let us see the objective of today's session is to know about the issues of thread. On the outcome of this session, the students may be able to understand the issues of thread, executing the thread. So here are the outlines of today's session. The issues are, first we'll see about fork system call and EXEC system call. Next we'll discuss about the signal handling process, then thread cancellation, thread local storage, and scheduler activations. So these are the 5 issues in executing the thread. We'll see one by one. The first one is fork and EXEC system calls. The fork system call is used to create a separate process, and it should be a duplicate process. That is, the fork, using this fork system call, the parent process will create a child process using the fork system call. So this child process will be the duplication of the parent process. Okay. If one thread in the program calls using the fork system call, does the new child process duplicate all the threads or a single thread? So this is the issue. Okay, to overcome this issue, some Unix operating system have chosen to have 2 versions of fork system call. The first version is this. The fork system call duplicates all the threads. The second version is that it duplicates only the thread that invokes the fork system call. Okay. If a thread invokes EXE system call, means the program specified in the parameter to EXE system call will replace the entire process, including all threads. That means EXE system call is always used to execute the instructions or the program of the child process. If the EXEC system call is called immediately after the fork system call, then it will duplicate all the threads, which is an unnecessary process, as the program specified in the parameters to EXEC system call will replace the process. So in this instance, duplicating only the calling thread is appropriate one. So no need to duplicate all the threads. If the EXEC system call is executed, it will execute only the child process program code. So it is not necessary to duplicate all the threads. If, however, the separate process does not call the EXEC after the fork system call, the separate process should be duplicating all the threads. The thing is that the fork system call is used to create a new child process, which will be the duplicate of the parent process. And EXEC system call is used to execute the child process. And what are using the program parameters specified in the program. Okay. The next issue of executing the thread is signal handling. So what is meant by a signal? It is used to notify a process that a particular event has occurred. The signal may be of two types. One is synchronous signal, asynchronous signal. So this type of signal will depend on the source and the reason for the event. So all the signals, whether synchronous signals or asynchronous, it will follow the same pattern. A signal is generated by the occurrence of a particular event. Second, the signal is delivered to the process. Once delivered, the signal must be handled. That is, first the signals will be generated. Second process, the signal will be delivered to the process. And third, once it has been delivered, the signal must be handled. Signal, let us see the signal handlers. A signal may be handled by one of the two possible handlers. The first one is default signal handler. The second one is user-defined signal handler. So every signal has a default signal handler that the kernel runs when handling the signal. Usually the signal will be having the default signal handler. User-defined signal handler will be called to handle the signal. So the signals are handled in different ways. Some signals are simply ignored. The case is that if you need to change the size of the window, that type of signals will be simply ignored. In other cases, the signals, some signals are handled by terminating the program. That is, if the signals are illegal memory access, they will be handled by terminating the program. So this what about the signal handlers? We have two types. One is default signal handler, and the other one is user-defined signal handler. Next, we are going to see the signals in single-threaded and multi-threaded programs. So handling signals in a single-threaded program is straightforward. So in this case, the signals are always delivered to the process. However, delivering the signals is more complicated in the multi-threaded programs, where a process may have several threads. So first, deliver the signal to the thread to which the signal applies. Next, deliver the signal to every thread in the process. Next, deliver the signal to certain threads in the process. Fourth, assign a specific thread to receive all the signals for the process. So these are all the things which we need to process in multi-threaded programs. So handling the signals in a single-threaded program is very straightforward and it's very easy. Always the signals are delivered to the process. So the handling the signals or delivering the signals is more complicated in case of multi-threaded programs. The next issue is thread cancellation, which involves terminating a thread before it has completed. For example, if multiple threads are concurrently searching through a database, one thread returns the result means the remaining threads might be cancelled. So if you're having more number of threads which are concurrently executed, if one thread returns the result means the remaining all other threads must be cancelled. Another situation, when the user presses a button on a web browser, that will stop loading the web page any further. So if it is also, the thread will be cancelled. So the web page loads using several threads, where each image is loaded in a separate. Loading of every image will be considered as a separate, executing the separate thread. So whenever the user presses a stop button on the browser, web browser means all the threads loading the web page will be cancelled. Okay, so this is the issue of thread cancellation. A thread that is to be cancelled is often referred to as target thread. Okay, so whatever the thread we are going to cancel it, we call that as target thread. The cancellation of a target thread may occur in two different scenarios. One is the asynchronous cancellation and the second one is the deferred cancellation. So what is mean by asynchronous cancellation? One thread immediately terminates the target thread means we call that as asynchronous cancellation. Deferred cancellation means if the target thread periodically checks whether it should terminate, allowing it when opportunity to terminate itself in an orderly fashion. This we call it as a deferred cancellation. The fourth issue of thread is thread local storage. So thread belonging to a process will share the data of the process. So this data sharing will provide one of the benefits of the multi-threaded programming. However, in certain circumstances, each thread might need its own copy of certain data. That is, each thread will need to have its own copy of certain data. Okay, we call that particular data, such data is called as thread local storage or a TLS. For example, in a transaction processing system, we may service each transaction in a separate thread, or each transaction must be assigned a unique identifier. That is, unique ID must be assigned for each transaction. So to associate each thread with its unique ID or identifier, we could use this thread local storage, that is TLS. The next issue is scheduler activations. A final issue to be considered with a multi-threaded program is that the communication between the kernel and the thread library. Here, the number of kernel threads to be dynamically adjusted to ensure the best performance. Many systems implementing either by many-to-many model or two-level model which plays an intermediate data structure between the user thread and the kernel thread. So this data structure mainly we call that as a lightweight process or simply LWP. Okay, the issue is that we need to maintain the communication between the kernel and the thread library in the multi-threaded program. So here you can see the diagram. This is the user thread and this we call it as LWP is a lightweight process, and here is K represents the kernel thread. We need to maintain the communication between the user thread and the kernel thread. So this is what the issue in the multi-threaded programming. So to the user thread library, a lightweight process appears to be a virtual. So this lightweight process will be acting as a virtual processor. Okay, on which the application can schedule a user thread to run. Okay, this is a lightweight process is a virtual processor which will assign the application can schedule the user thread to run. Each LWP, that is lightweight process, is attached to the kernel thread and run on a physical processor. This lightweight process is a virtual processor which is attached to the kernel thread on which the user thread is run on the physical processor. If the kernel thread blocks, then automatically the LWP virtual process also blocks, and automatically this user thread will also be get blocked. So when the kernel thread is waiting for the IO operation need to be completed, the kernel thread will block means LWP, this virtual processor, will also get blocked. In turn, this user thread will also get blocked. So this is a chain process. Up the chain, the user level thread attached to the LWP also get blocked. So this is the reference used for preparing the slides. Thanks for watching. Thank you.